Chapter 2.7, Graphing Techniques. Transformations are obtained by taking a basic graph, and we know our basic shapes, right? And shifting it horizontally or vertically, reflecting it over an axis, or stretching or shrinking it. It will still remain the same basic shape, but it may be in a different location, upside down, fatter, skinnier. We're going to discuss the absolute value function for our example, but this applies to all of our basic functions. Okay, we know that the absolute value function, f of x equals absolute value of x, has the basic shape of a V. So if I'm just trying to get my basic points, what I'm always going to do is just think about plotting maybe the points -2 through 2. And again, I'm just plugging into this basic function. So if I let x be -2, the absolute value of -2 is 2. If I let x be -1, the absolute value of -1 is 1. If I let x be 0, absolute value of 0 is 0. And if I let x be 1, absolute value of 1 is 1. Absolute value of 2 is 2. And I get several points I can plot. -2, 2. -1, 1. 0, 0. 1, 1. 2, 2. And notice I do see that I get that V shape. Okay, let's see what happens if I were to plot, instead of absolute value of x, let's do absolute value of x plus 3. Okay, if I plug in some points, then I have absolute value of -2 is 2 plus 3 is 5. Absolute value of -1 is 1 plus 3 is 4. Absolute value of 0 is 0 plus 3 is 3. Absolute value of 1 is 1 plus 3 is 4. Absolute value of 2 is 2 plus 3 is 5. So I can plot these points. -2, 5. -1, 4. 0, 3. 1, 4. 2, 5. Notice I still get that V shape. It's just in a different location. And notice what that location is. It is just this graph, except every point was moved up 3. Every one of the points from my original graph was moved up 3. Up 3. Let's see what would happen if that plus 3 were inside the absolute value bars. I'm going to start with the same idea, plot a bunch of points, but this time -2 plus 3 is 1, absolute value of 1 is 1. -1 plus 3 is 2, absolute value of 2 is 2. 0 plus 3 is 3, absolute value of 3 is 3. 1 plus 3 is 4. 2 plus 3 is 5. And I get these points. So I have -2, 1. -1, 2. 0, 3. 1, 4. 2, 5. And look, it looks like a straight line. I don't see my V shape at all. But because I know it has to have a V shape, I've got to come over here and plot some more points until I find that V shape. If I plug in a 3, 3 plus 3 is 6. Well, that's not helping me. Let's go back up and plug in maybe -3. -3 plus 3 is 0. So I'll get negative 3, 0. Still not helping me. Let's try negative 4. Negative 4 plus 3 is negative 1. Absolute value of negative 1 is 1. Okay, a little help there. Let's try negative 5. Okay, negative 5 plus 3 is negative 2. Absolute value of negative 2 is positive 2. Negative 5, 2. If I were to plug in negative 6, I would get negative 3, and the absolute value of negative 3 is 3. Negative 6, 3. Now I see my V shape. And if I were to pay attention or notice what happened between my original graph and this one, every single point is moved left 3 units, moved left 3 units, moved left 3 units, moved left 3 units. Notice this plus 3 moved it up 3, but a plus 3 in here moved it backwards. Okay? Anytime my values are inside with the x, it's going to appear to do the opposite. It really does the opposite over here also, but it's affecting the y value, and if I move this number over here, see, I've already changed the sign of that number by having it on the opposite side of the equation from my y. So it really does the same. It just appears to do something different. All right, so what that tells me is any numbers that are being added or subtracted are going to just shift my original function right and left or up and down. Those are called translations or slides. It just slides the graph up and down. If the number's outside, it affects the y, right? Or horizontally, if the number's inside, it affects the x. Let's try that again. Our basic shape, remember, I can get very easily by plugging into just the absolute value. So my goal is I want to be able to come over here and get the basic shapes without doing anything, right, for all of my basic functions. And it's just plugging in for most of them, negative 2 through 2, and doing one operation. So I don't even have to draw this chart. I can come in and say, oh, well, the absolute value of negative 2 is 2. The absolute value of negative 1 is 1. The absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. And there's my basic shape. Okay, let's see what happens if we have a number being multiplied as opposed to added. So what if we had 3 times the absolute value of x? Well, let's try this. Let me change colors. Now let's try our basic points again. Absolute value of negative 2 is 2 times 3 is 6. Absolute value of negative 1 is 1 times 3 is 3. Absolute value of 0, 3 times 0 is 0. 3 times 1, 3 times 2, and I get these points. Negative 2, 6. Negative 1, 3. 0, 0. 1, 3. And 2, 6. Notice I still have a V shape. It's just skinnier, right? We call this being stretched. And again, we're talking about the function being stretched. And f of x is y. So imagine if you had a piece of gum and you stretched it this direction, what would happen to it? It would get skinnier. Okay, so when you see the equation, it's obvious, should be, that numbers larger than 1 are going to stretch it. But a lot of times when people see the graph, it's confusing because they think that's shrunken. But we're talking about stretching it up and down the y-axis, so pulling it up, which would make it skinnier. If I had a value here that was a fraction, right, a proper fraction, then it's going to shrink it, right? In other words, it would make it fatter. Okay, numbers inside with the x appear to do the opposite, right? So notice what we had here. If I took every one of these points and multiplied it by 3, my y value, outside, it's not inside with the x, it's affecting the y value. So I would take my y value and multiply it by 3, means I would jump up here. This y value is at 2. If I multiply it by 3, 2 times 3 is 6. This y value is at 1, multiply it by 3, gives me my point. This y value is at 3. 3 times 3 is 9, gives me my corresponding point. Okay, now here's every possible thing that could happen with an absolute value function, right? We could have numbers here, 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 here. We must do these transformations in a certain order. Sometimes the order doesn't matter, but because sometimes it does, we must always do them in a certain order to get the correct answer. And you're going to do this first, this second, this third, and your vertical translation last. All right, so don't forget that order. Once again, this is going to move right and left, right, and in the opposite direction of whatever sign is here. This is going to stretch or shrink it according to your x values. This will stretch or shrink according to your y values, and this will move it horizontally. If you have a negative in front, or in here, right, a negative, it's going to be a reflection. It's going to flip it over one of your axes. Okay, so absolute value of negative 2 is 2, but then I would have negative 2. Absolute value of negative 1 is 1, negative 1. 0 isn't positive or negative. Then negative 1, negative 2. So plotting these points, negative 2, negative 2, negative 1, negative 1, 0, 0, 1, negative 1, 2, negative 2. And this is a reflection of the y-axis. It's flipped over the x-axis, but it's a reflection in the y-axis. If the negative was in here, it would be a reflection in the x-axis. It would flip over the y. With the absolute value, you can't even tell that that has happened, right? Because this graph is symmetric about the y-axis, and we'll talk some more about symmetry at the end of this lesson. But these steps apply to every one of our basic shapes. So we're going to go do several examples. Now, a caution for you. The way your homework treats these, if you don't do the translations on your own, by hand, when you get to a test, you're not going to be able to do them. Because mostly it's just going to ask you what translation has been performed. Has it shifted right 3 units, up 3 units? Is it stretched? Is it reflected? It's just going to ask you that, and it doesn't really ever make you graph them. So make sure that you practice plenty of physical graphing of these translations. All right, so let's do some. All right, let's say we want to graph f of x equals x squared minus 2. Well, I know it's going to be a parabola. It's just going to be shifted down 2 units. The first thing I have to do is get my basic points. Now, I'm not really graphing just x squared like I did on the previous page. So instead of putting dots there, I'm going to put little x's because I don't want to confuse the points on my basic shape with the points I'm going to connect to draw my graph. So again, one time or two more, I'm going to show you what we're doing. We're basically imagining plotting these points, except instead of taking the absolute value of them, I'm going to square them. So negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. I want to be able to get those points very easily, very quickly. And then I'm going to take every one of those points and I'm going to move them all down 2 units. Now that's actually what I'm graphing, so I'm going to make that a point. Down 2, down 2, down 2, down 2. And here, now don't make it a V because it's a parabola, so make it a U shape, is the graph of this function. Let's try that again. Okay, so if I have f of x equals x minus 2 all squared, my basic points are the same because it's an x squared. It's a parabola. So negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. I want to be able to get these points very quickly. Just go over and draw them. Now, because this is inside with the x, I know it's going to affect the x-axis. It's going to slide back and forth, but it's going to appear to move in the opposite direction. So instead of moving left 2, I'm going to move every one of these points right 2, right 2, right 2, right 2, right 2. And draw in my parabola. Okay. Let's do x equals 1/2 times x cubed. This time I know it's going to be this basic shape, but it's going to be shrunk. All right, so I need my basic points first. I'm going to start doing them in different colors just because of the nature of what this looks like. But remember, on your graphs, you'll have little X's for your basic shape and then points for the points that are actually on your graph. So I'm going to go through negative 2 through 2, except just cubing them. Negative 2 cubed is negative 8. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. So if I were just graphing x cubed, there are my points. And I know, don't go diagonal across there, make a little hump. Except I'm going to take half of every one of those y values. Half of the y values because it's not inside with the x. So my y value is at negative 8. Half of that jumps me to negative 4. My y value is at negative 1. Half of that jumps me to a half. Half of 0 is still 0. Half of 1 is a half, and half of 8 is 4. It's still that same shape, except it's been shrunk. Okay, let's try f of x equals, let's do the square root of x plus 4 minus 1. Okay, this is the only one that I'm not going to use the basic points -2 through 2. Let's think about that and see why. If I were doing just my basic function, the square root of x, and I put a -2 in here, that's a complex number, right? An imaginary number. So I'm not going to do my negatives. I can do the square root of 0, square root of 1, but the square root of 2, that's an irrational number. So I don't want to do it. Square root of 3, no, but square root of 4, hey, I can do that. Square root of 5 is an irrational number. Square root of 6, square root of 7, square root of 8. So my next one is square root of 9, which is 3. So these are my basic points for my radical. And I can still start with -2, but when I start over here and think, oh, square root of -2, wait, imaginary, not on the graph. Square root of -1. Square root of 0 is 0. Square root of 1 is 1. Square root of 2 is not a whole number. Square root of 3, oh, square root of 4 is 2. Square root of 5, no. Square root of 6, square root of 7, square root of 8. Square root of 9 is 3. And here's that shape that I know it needs to have. Do go out to this point. Don't stop here, right? People tend to not curve back over with that. So I need these points, except I'm going to move everyone left 4, opposite direction when it's inside with the x, and down 1. So I'm going to take this point and I'm going to go back 1, 2, 3, 4, and down 1. This one's going to go back 1, 2, 3, 4, and down 1. This one's going to go back 1, 2, 3, 4, and down 1. This one's going to go back 1, 2, 3, 4, and down 1. And then there's my graph. It's the exact same shape, except it's been slid back 4 and down 1. All right, let's use this grid, and maybe let's do f of x equals 2 times the absolute value of x minus 3 plus 1. Okay, so my basic points are just for absolute value. Absolute value of -2 is 2, absolute value of -1, absolute value of 0 is 0, absolute value of 1 is 1, absolute value of 2 is 2. I'm going to take every one of those points and move them to the right 3. I'm going to multiply the y value by 2 and then move it up 1. So I'm going to go right 3, 1, 2, 3. I'm going to multiply this y value by 2, so 2 times 2 is 4, and then go up 1. This point got translated to this position. Same steps for every one. I'm going to move this point right 3, 1, 2, 3. My y value is at 1, so if I multiply it by 2, it changes the y value to 2, and then it goes up 1. Move this one right 3, 1, 2, 3. Multiply the y value times 2, but the y value is 0, so 0 times 2 stays there, and then it goes up 1. Move this point right 3, 1, 2, 3. Multiply the y value, which is 1, times 2, so it changes to 2, and then goes up 1. Okay, move this point right 3, 1, 2, 3. The y value is 2, so 2 times 2 is 4, and then up 1. And there is my graph. Okay, let's do f of x equals negative cube root of x minus 2. Cube root of x, I think I may have mistakenly said this is the only one I don't use negative 2 through 2 on. Cube root is another special one. Again, once we get used to these points, because I can't take the cube root of 2 or the cube root of 3, so I'm going to start with the cube root of negative 8 because that's the first one that I can do. It's negative 2. The cube root of negative 1 is 1. The cube root of 0. The cube root of 1 is 1. And the cube root of 8 is 2. So I just have to get used to how am I getting these points. And notice it's got the same shape as the cube, except it's just laying over on its side, right? So I have the opposite values. Over here I use 2 at negative 2, negative 8, negative 1, negative 1, 1, 1, 2, 8. And here I do the opposite, negative 8, negative 2. Okay, except I'm going to take every one of those values and I'm going to multiply by negative 1, or, so really having a negative here, the operation is no different than having any number there. I'm going to multiply the y value by negative 1. However, I could just think about it as flipping. Instead of being a negative 2, it's positive 2, right? Oh yeah, negative 2 times negative 1 is positive 2, but then I need to go down 2. So I'm going to flip this one over, or negative 1 times negative 1 is positive 1. But then I'm going to go down 2. Negative 1 times positive 1 is negative 1, but then I'm going to go down 2. Okay, now my y value is at 2, so if I multiply it by negative 1, it gives me negative 2, but then I'm going to go down 2. And I have to fill in, I didn't do 0 down 2, and I have to fill in that shape that I know it has for my cube root. So be sure and practice drawing the actual graph on these things. Your homework does not do a sufficient job of that. All right, let's talk about symmetry before we finish up here. We mentioned that my absolute value graphs and the parabolas are symmetric with respect to that, well, imagine that's a straight line, with respect to that y-axis, right? That y-axis. In other words, I could fold them over that y-axis and they should lay on top of themselves. So we're going to sometimes be interested to know if our graph is symmetric with respect to the y-axis, with respect to the x-axis, or with respect to the origin. To determine if a graph is symmetric with respect to the y-axis, we're going to replace x with negative x. If it does not change the equation, it's symmetric with respect to the y-axis. To determine if it's symmetric with respect to the x-axis, replace y with negative y. If it does not change the equation, it's symmetric with respect to the x-axis. To determine if it's symmetric with respect to the origin, I'm going to replace the x and the y with negative x and negative y. Okay, so let's practice this one. Determine if this equation is symmetric with respect to the x-axis, the y-axis, the origin, or none. So first of all, if I'm going to check x-axis symmetry, right? X-axis, I had y listed first here. So I'm going to do x-axis symmetry. I'm going to replace y with negative y. So in this equation, I'm going to make this negative y equals x cubed minus x, and then solve it back for y. So multiply everything through by that negative. Y equals negative x cubed plus x. Is this exactly the same as that? Nope. Well then no, it's not symmetric to the x-axis. Let's see if it's symmetric to the y-axis. To see if it's symmetric to the y-axis, we're going to replace x with negative x. So I'm going to take this equation, but instead of x, I'm going to replace everything with negative x. Okay, and then simplify it. Well, a negative cubed is still a negative, and a negative is a positive. And decide, is this exactly the same as that? Nope. Well then, it doesn't have y-axis symmetry. Let's see if it's symmetric with respect to the origin. I'm going to replace the x and the y. So I'm going to take this equation and I'm going to say negative y equals negative x cubed minus negative x, which is negative y equals negative x cubed plus x, and then multiplying or dividing by that negative 1 to get back to y, x cubed minus x. Is this identical to that? Yes, this one is symmetric with respect to the origin, right? So yes, symmetric with respect to the origin. Notice an equation can be symmetric with respect to the origin without being symmetric with respect to the x-axis or the y-axis. But if you have an equation that is symmetric with respect to the x-axis and the y-axis, it must be symmetric with respect to the origin. So if I've checked both of these and gotten a yes, I automatically know it's also symmetric with respect to the origin. However, just because it's not symmetric with respect to x and y axes does not mean it's not symmetric with respect to the origin. If our equations are functions, then we have particular terms for our symmetries. An even function is a function that's symmetric with respect to the y-axis. And an odd function is a function that's symmetric with respect to the origin. A function cannot be symmetric with respect to the x-axis, right? Think of the vertical line test. If it's symmetric with respect to the x-axis, it would look something like this, and therefore it's not a function. So by simply being a function, we've already ruled out symmetry with respect to the x-axis. So let's try that again. It's the exact same steps from before. Let's say we want to know if f of x equals x squared plus 2x is an even function or an odd function. Okay, to determine if it's an even function, I'm going to see if it's symmetric with respect to the y-axis. That means I'm going to replace x with negative x. So f of negative x is negative x squared plus 2 times negative x, or x squared minus 2x. Is this identical to this? Then no, it's not even. Let's see if it's odd. To see if a function is odd, it's the same thing as checking symmetry to the origin. which means we're going to replace negative x and negative y, which means I might want to rewrite that instead of f of x. Remember, I can always change that to y. So negative y equals negative x squared plus 2 times negative x, or negative y equals x squared minus 2x. Getting rid of the y, I'm getting rid of the negative in front of the y equals negative x squared plus 2x. Is this equation identical to the original? No. This one is neither even nor odd.